Okay, good. So, so this lecture I was going to go back to the just the main subject of asymptotic symmetries, and discuss the best known example of an asymptotic symmetry group that's actually interesting, which are the asymptotic symmetries of ADST. So this work was actually first done by Brown and Ano in a paper in 1986 using Hamiltonian formalism. That paper is a bit hard to read, so I guess I'm going to do something a bit simpler than what I did. And of course, as I said, so as I mostly emphasized in the first lecture, the asymptotic symmetries of a space-time should become the just the usual symmetries of the dual field theory in holography. So what you should be seeing are the symmetries of the dual CFT. So this would be a check of ADS3 CFT2. And in order to explain what we expect to see, I'm going to start with a quick review of ADS. So D+1. Then a quick review of CFT, very quick, and in particular for D222, where something nice happened. I guess most of you know that there's an infinite symmetry enhancement in two-dimensional CFTs, but okay. Hopefully some people will get something out of it. Okay, so let me just briefly tell you about ADS. So this is a D+1 dimensional anti-de Sitter spacetime. So its definition is that it's the maximally symmetric spacetime of negative curvature. So there's a classification of spacetimes by the number of isometries that they preserve. And for example, flat space is a maximally symmetric spacetime, and you can count how many isometries it has, and in n dimensions it's n times n plus 1 over 2. That's the maximum you can have. And okay, because it's maximally symmetric, the curvature has to be constant. But you get one example of zero curvature, of positive curvature, and of negative curvature. And of course, those are flat space, de Sitter, and anti-de Sitter. So when it has maximal isometry, the Riemann tensor is entirely determined by the metric. So it looks something like this. So for negative curvature, it looks like this, where L is called the radius of anti-de Sitter. There's something like G mu sigma sigma. And this form is basically dictated by the symmetries and anti-symmetries of the Riemann tensor. So this is the only thing that you can write down just in terms of the okay. So the isometry group of anti-de Sitter space in D+1 dimensions is SO D,2. So you can check. So if you're trying to count the generators, so this is an SO group. So I'm going to have D+2 so it's generated by, well, so these are matrices that live invariant the form eta tilde mu nu, which is something like minus and a bunch of pluses, the order. Right? So this is similar to as you know, the rotation group lives invariantly the identity, so lambda transpose times lambda is the identity. For the Lorentz group, it lives invariant the eta with 1 minus and a bunch of pluses. This S of D, 2 lives invariant this thing. This, okay? So you can write it like this. So, but you can do the counting the same as for S of D plus 2. And that you know that is generated by antisymmetric matrices. So you can just do the counting and antisymmetric matrices. This many. So you see that this number is equal to that number for n equals d plus 1, the number of dimensions of the space. Was this argument clear, what I just said? Okay. So, okay. And, okay, so using this, the simplest way to define antidesical spacetime is actually by embedding it into Minkowski. Well, it's not actually Minkowski. So you can embed it into some spacetime which has a signature minus, minus, plus, 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 and so on. So it's RD, 2. So it's like Minkowski, but with 2 time directions and the spatial directions, where the metric is just given by this. And you ADS, okay, so the metric for this spacetime is just d tilde squared, which is just eta tilde. Okay, let me call this indices. So the d plus 2 dimensional indices, I'm going to call them m and n. So n, dxn, dxn. So as you see, this line element is manifestly invariant under S of D, 2, just by construction, because I'm using this particular metric, which is invariant. Okay. And ADS is defined as the locus on which xn times xn times eta tilde and n equals minus 1 over x squared. Okay. So this is a hyperboloid embedded into this this particular RD, 2 space. So it's going to give you a D plus 1 dimensional spacetime, and the S of D, 2 invariance is built in because this condition is S of D, 2 invariant, that you can easily see. Because the metric is S of D, 2 invariant. And then good. And then people write embedding coordinates. So you can write the metric on ADS in this way, but then you have a constraint, or you can just introduce coordinates until the constraint is automatically solved for. And these coordinates are something like this. And force rho, force tau, x1, and force rho, sin tau, and then x r l sin rho omega I with some omega squared equal to 1. So this axis, so for I goes from 1 to d, this axis automatically satisfies this constraint. Why? Because this thing is nothing but minus x naught squared minus x1 squared plus sum over the other i's. Okay. I'm going from 2 to d plus 1, right? Of x I squared.
Sorry. I'm concerned with your definition of the xn eta tilde equal minus 1 over L square. L is the length.
Yeah.
Should not be minus L square.
Right. I guess when we did the calculation, we have noticed that, yeah, you're right. It's it has dimensions of legs. Okay, so when you plug in this, you see that this constraint is automatically satisfied because this thing gives you an L squared cos squared, and this thing so with a minus, and these guys will give you plus L squared sim squared. So so you do get a minus L squared in the end. So these embedded coordinates automatically satisfy this constraint, and then you plug them into this this expression for the metric, and you find what the induced metric on anti-de Sitter is. And what you find is something like this. S squared minus cos squared of rho tau squared plus d rho squared plus sin squared of rho omega squared d minus 1. So let me see. So here, so you have a radial coordinate, you have a time coordinate, and here is the metric on the d minus 1 sphere. This omega squared that you get from this omega s. And you have to be a little bit careful about uncompactified time because here you have 2 times. So you need to make the time coordinate non-compact to do this. But okay, so this is the metric of a global d plus 1 anti-de Sitter space. So this metric actually covers the entire space. And if we wanted to draw a picture of what the spacetime looks like, yeah, I guess you can see, hopefully. So it's useful to introduce a new coordinate theta via cos rho equals 1 over cosine theta. So cos goes between 1 and infinity for a rho going between 0 and infinity. And this is okay because so rho equal to 0 will correspond to theta equal to 0. And rho going to infinity corresponds to theta equal to pi over 2. Where the cosine goes to 0. So we have theta in between 0 and pi over 2. Okay. And if you do this substitution, you plug it into this metric, then you can write the metric as follows. L squared over cosine squared of theta minus d tau squared plus d theta squared plus sine squared of theta d omega squared d minus 1. So this is just, okay. This first term is obvious, it just comes from the definition, then you have to compute the rho in terms of d theta, you're going to get this, and simply, again, it's simple. It's just 2 lines of algebra. But the nice thing about having written the metric in this way, so here the problem with this metric is that, as you see, the spacetime is infinite. So when I send rho to infinity, the metric blows up. Here, when I send theta to pi over 2, again the metric blows up, but it blows up in a very special way, in the sense that if I rescale the metric by a conformal factor, so if I send g to say lambda squared times g for some judiciously chosen lambda, then the metric doesn't blow up anymore. Okay. So if I multiply the metric, for example, by cos squared of theta, this conformal rescaled metric here in parentheses doesn't blow up, and I can actually draw it on the board. Okay? And what I get? Well, what I get, so let me set d equal to 2 such that I can actually draw it. Okay? So this is actually going to be a circle, 5 squared. And this, well, it looks a bit like the metric on the sphere, but it's not a sphere, it's half a sphere, as you can see from here, because theta only runs between 0 and pi over 2, which is the same as this. So what I'm going to get, so this is going to be the metric on this, then I have the time coordinate parameters. Tau, so theta goes from 0 to pi over 2 at the boundary, and then the boundary, it's an S d minus 1, and I've only drawn the case where it's an S1.
I'm a bit confused about the range of the time coordinate. So is it from minus infinity to plus infinity?
Exactly.
But when you define this,
yeah, so you have to look at the universal cover. This is so you start with tau, which is identified with 2 pi, but then you have to uncompactify it.
Think about the toilet paper. It's an analogy. I think walking like this analogy first.
Okay, I guess, yeah. Okay, and I should say that, well, I'm assuming most people are familiar with this, so this is a common trick that is done in order to be able to put an otherwise infinitely extended spacetime on, to be able to draw it. You always look for coordinates where the metric looks like a metric where, where the coordinates have a compact support up to an overall conformal factor, which takes care of the fact that the spacetime is infinite. And the nice thing about this conformal rescaling is that obviously the behavior of light rays is unaffected by me multiplying the metric by some factor, because light rays always travel, always satisfy this relation. So if I multiply my metric by some factor, it doesn't matter for light rays. So I can use this diagram to figure out what light rays do in it, but otherwise for computing distances, of course, it's not very good, because both time-like and space-like intervals are actually affected by that. But the causal structure is not, because this doesn't care about this. Okay, so this is everyone's picture of anti-de Sitter spacetime. So it looks like an infinitely extended cylinder in time, and then something like that. Good. And so I said, so these are the global coordinates which cover the entire spacetime, but oftentimes people talk about Poincaré coordinates. And what's nice about them is that they make certain isometries very manifest. So the metric of ADS in Poincaré coordinates looks something like this. Eta mu dx mu plus dz squared over z squared, where this is the metric on Minkowski, so it's on R d minus 1, 1. Okay? So for example, I don't know if people are familiar, so there's this long review of ADS-CFT by Maldacena, Oz, a bunch of people, the Magoo, the famous Magoo. Okay, so Maldacena, is this a Haroni? Gupser, Oz, Oguri, and Oz. Okay, so this is a review from 99, I guess. So you can find all of these formula very nicely written there. The embedding coordinates for global. You also find the embedding coordinates for Poincaré that give you this metric through basically identical argument. But Poincaré coordinates do not cover the entire spacetime. So they only cover something like this, a patch like that on the boundary. And okay. But what's nice about them is that they make a lot of the isometries manifest. So for example, so I told you that the isometry group is SOD, 2. This part of the spacetime is SOD minus 1, 1. And then you can see like you have an obvious scaling symmetry of the spacetime here, which is z goes to lambda z and x goes to lambda x, that you can also see very nicely, and so on. So that's another. Okay, good. So this was a very quick review of anti-de Sitter spacetime. So now let me give an equally quick review of what CFT is. So CFT is a conformally invariant quantum field theory, and I'm taking the dimensions. So what does it mean that the QFT is conformally invariant? So first of all, it's Poincaré invariant. So I have the Lorentz group. So this is SO P minus 1, 1 plus translations. So these are the P mu. Let me call the generators of this N mu. Okay, so the reason that I've written for you here the Poincaré metric is that you see very clearly how ADS in these coordinates realizes this Poincaré symmetry, because it's obvious that the metric is Lorentz invariant and also translational invariant. But it also has more interesting symmetry, so it has scaling, dilatations, under which the coordinates go x mu to lambda times x mu. And again, ADS in this form very clearly has that dilatational symmetry. You just have to scale z at the same time as z. And then it has the special conformal. Generators K nu, which are a bit harder to see. They basically correspond to spacetime inversions. So something like, actually I didn't write it down, but it's mu. Okay, I wrote the infinitesimal version, but it's x goes to x over 1 plus dx, something like that. Yeah.
I have a question because it seems that this is an argument for ADSFT because we have a matching on the symmetries.
Mm-hmm.
But the symmetry here is the symmetry, the isometries of the spacetime. But it should be the isometries of maybe of the theory we're going to put in the spacetime.
Right. So
I've seen this argument many times. And
yeah, you're entirely correct. So this argument. So as I how to say, emphasize in the first lecture, what we should be matching. So thank you very much for this comment. What we should be matching are the asymptotic symmetry. So we have this theory of gravity on some spacetime manifold n, and we have some field theory on delta n. What we should be matching are the asymptotic symmetry of this gravitational theory with the global symmetries of the field theory. Okay? So you're entirely right that what we're discussing here are the isometries of the vacuum ADS solution. So what are the asymptotic symmetries? So the asymptotic symmetries is that I take any field configuration in my gravitational theory. It doesn't have to be the vacuum configuration. So any asymptotic ADS spacetime where I have to specify what asymptotic ADS means. And I compute the asymptotic symmetries for all this set of geometries. And, well, I find what it is. And I compare that with the symmetries of, in this case, the conformal field theory, which obviously act on arbitrary states. I don't have to be in the vacuum. So this is a very good point. It turns out that the asymptotic symmetries, maybe this was also your question, asymptotic symmetries don't really care what theory of gravity. So this is why it's not theory dependent, really. They only depend on the asymptotic structure of the spacetime. And this is why you get universality, is because any theory of quantum gravity that you decide to put in ADS is going to give you some sort of suit, if the theory is consistent. And that's because the asymptotic symmetries don't really depend on the theory, but on the structure. Okay, and just to emphasize the point, this is precisely what we're going to see in the case of ADS3, where the asymptotic symmetry group is infinite dimensional, is not the isometry group of the vacuum spacetime. So, yeah. Okay, but here, how to say? This is a simple argument that everyone uses, but more correctly, we should be talking about asymptotic symmetries of d+1 dimensional anti-de Sitter. What happens is that for d greater than 2, so ADS4 and higher, the asymptotic symmetries of the spacetime coincide with the isometries of the vacuum. So we can just talk about that, but yeah, it's not entirely. And in ADS3, something else happens. Okay. I have to tell you also what conformal transformations are, I guess. so maybe just to define what conformal transformations are. So conformal transformations are coordinate transformations such that so x mu goes to some x prime of mu, which are some functions of the original coordinates, such that the new metric is some conformal factor, lambda squared, times the old metric. So if before I was in flat space, well, so the new metric has to be conformal. Okay, so we can actually see all these transformations. Just so if we start with the flat metric eta mu, so under some coordinate transformation, x mu goes to x mu plus c mu of x. So we're just doing this infinitesimally because it's easy. Then delta c of the metric is equal to just the derivative, which for a flat metric is just this. Okay. Up to minus sign. I guess maybe there's a minus sign. I'm not going to care. So we want this to be lambda squared times eta mu delta. Something like that. Okay, so the solutions to this are, well, in the case of translation, so if you take c to be constant, then you actually get zeros, and these are the translations. So we have the transformations that leave the metric entirely invariant, so this thing is 0. And those are for c constant, which gives the translation. And for c, so this is obviously a solution. Translations. Then you have omega mu x mu with omega antisymmetric in its indices. This again solves this equation with a 0 on the right hand side, and those are nothing but the Lorentz boost and rotations. Okay, but then we get some more interesting solutions that actually turn on a non-trivial conformal factor here. and these are the dilatations. So lambda x mu. So you can see from here that you're going to pick something like d mu of x lower mu gives you a factor of the metric with the lambda in front. So this is going to end up being proportional to eta mu. So these are the rescalings. And then the special conformal transformations look something like d mu x squared minus 2 x mu d mu x mu. You can see that this equation, that this guy is proportional to eta mu nu, also has a solution that looks like this. And these are the infinitesimal generators of the special conformal transform. Okay, and okay, so this is all very nice. So it turns out the conformal field theories are really beautiful quantum field theories because, in particular, you can study them. So conformal invariance imposes a lot of constraints on the form of correlation functions. So 2 and 3 point functions are entirely fixed by conformal symmetry up to some constants, and then you can actually reduce high point correlation functions to lower point ones using something known as the operator product structure, which is particularly convergent. So these are very, very nice types of quantum field theory, which can actually be studied as strong coupling. So people like them a lot. But actually, I won't go into that. What I wanted to tell you about is what happens to the conformal group in 2 dimensions, because this is a bit special. So this is in general dimension, and I mean, how should I say? You can count generators and you can compute the commutators of the symmetries to find that the conformal group, sorry, I should say this, the conformal group is SOD, 2, which is identical to the isometric group of the ABS space, which, as was pointed out, is not quite the correct argument for holography, but it goes against along the lines. Okay, good. So now let's look a little bit at the conformal group in 2D. And there it turns out that it's very useful to introduce light-like coordinates. So x plus minus, which is x plus minus t. And in this case, the matrix of ds squared, which is minus dt squared plus dx squared, equals dx plus dx minus. So eta in these coordinates is 0, a half, 0. If I try to write it as a matrix, this eta mu. So if I try to solve for the conformal, so what are the allowed conformal transformations of the metric? So I solve d mu c mu plus d mu c mu is proportional to eta mu nu, but eta mu nu only has a plus minus component, right? So this is plus minus. So I find that d plus c lower plus equals d minus c lower minus equal to 0, because those components of eta are 0. And the plus minus part of this equation can be anything, because I just have a proportionality. Okay? Is it clear to you? Yeah. Okay. So what this implies, but then now you see what's nice. So okay, xi lower. So this implies the xi lower plus, and using the metric, I can write this as a half c upper minus, because the metric is off diagonal. The plus of it is 0, so it means it can be an arbitrary function of x minus. And similarly, C minus, which is a half C plus. D minus of it is 0, so it can be an arbitrary function of x. So unlike in higher dimensions where we can count on our fingers how many parameters we have here, we have d times d minus 1 over 2 plus just a finite number of parameters. Here, when you expand this function, for every Fourier mode, you get one symmetry. So you have an infinite dimensional conformal symmetries in 2 dimensions. Okay. Okay, so it's useful to get some representatives. So on the plane you can call. So I'm going to call. Okay, this is not very useful. Still, okay. I'm going to call the guys that depend on x minus the right movers. Why? Because this is killed by d plus, and d plus is dt minus dx. So you see that it's moving in a particular direction. And these guys who cannot see, but they were depending on x plus, I'm going to call them the left movers. Okay, so I can write some. So now I'm expanding this functions, arbitrary function of x plus and x minus in some basis. So one useful basis, for example, is just polynomials. So I put an index m to tell me which polynomial I'm looking at. And so I have x plus to the m plus 1 t plus. So of course these are vectors. These are the coordinate transformations. And C right m minus m plus 1 minus. And one can compute the Lie bracket algebra of these vectors and finds something like, so let me just write the algebra of the associated generators. So you find something like Lm, which corresponds to this C. Yeah. So these guys are going to correspond to the L's with an M, and these guys are going to correspond to L bars with an N. So you find something like Lm with Ln is m minus n, Lm plus n. And sorry, I have to erase this because also these guys correspond to L bar. Okay? So this algebra is known as the Guica algebra. Okay, so just some. So you have an infinite number of generators labeled by MN, and this is how they commute. And you have an identical thing for the right movers. I won't write it down, but the L bar satisfy asymptotic. Some special transformations here. So if you look at M equals plus minus 1 and 0. So for both L and L bar. So those are 6 generators, and actually they are the generators of SO22. So Lm and L bar M. For these values, these are the generators of SO22, which has 6 generators, which is just the global conformal group. So this is the 2-dimensional analog of these guys that could be written in any dimension. they are generated by the L and L bar ends for these values. And we can easily see who they are, because for n equals -1, you get del plus and then minus. So this is L1, L minus 1 and L bar minus 1. And what are these? These are the translation generators. So these are L minus 1 and L bar minus 1. But you sort of pair them into translation along one like direction versus the other like direction. For n equal to 0, you get x plus, b plus, and x minus, b minus. So this is sending x plus to something times x plus, and x minus to something times x minus. And what these guys are, okay, so x plus going to, say, lambda 1 x plus. This is actually a combination of dilatations and Lorentz. Why? So dilatations just acts on both coordinates, and x mu goes to lambda x mu. Whereas the Lorentz group, the way it acts on the light-like coordinates is by x plus minus goes to, say, lambda tilde plus minus 1 x plus minus. So if you take the usual formula for the boost, which on x and t, or t and x, acts like something like cosh, sinh, cosh, and instead you act with it on the light-like coordinates, which are x plus minus t, you find that at the level of the light-like coordinates, this thing just acts like multiplying x plus by a constant and dividing x minus by the same constant. So you see that these L naught and L naught bar generators, L naught corresponding to doing a simultaneous dilatation and boost such that only x plus changes and x minus stays invariant, and L naught bar corresponds to doing a different combination of dilatation and boost such that x plus stays invariant and x minus changes. So this is their significance. And then again, L1 and L bar 1, they're special conformal generators. They enter here, and I don't have a particularly intuitive way to think about this. Okay, good. So this is the width algebra. Okay, so far we just talked about classical conformal symmetry. So if I give you a classical conformally invariant action in 2 dimensions, it's going to have the symmetries. Now you might know that quantum mechanically it may be not possible to preserve some symmetries that are present classically. Those are known as anomalies. And here there is indeed a conformal anomaly. So when you quantize the theory, it's not possible. This sort of conformal symmetries are a little bit broken by your quantization procedure. The fact that you need to introduce a regulator in order to make sense of the theory. And what this does, it adds a central term to this algebra. And the central term is C over 12 m times m squared minus 1 delta m plus n 0. And similarly for the bar generators, I won't write it down. And this thing is known as the Virasoro algebra. Okay, so notice a few things. So this what do I want to say? So the first thing to notice is that the central term does not affect the global conformal generators, which were the values for m equals plus minus 1 and 0. You see that this term vanishes in those cases. So this only affects the higher LMs. This term is associated to some anomalous transformation of the stress tensor of the theory under conformal transformations. I don't really have time to go into it, but there's a full, beautifully done discussion in Di Francesco, which I guess everyone, if you haven't read it until now, you should read it. But anyway, so the full discussion is in Di Francesco, and they explain how all of this comes about and so on. But I won't get into it. I'm just telling you that it is some non-trivial calculation to actually show that there's this sort of anomaly term that appears in the algebra of the conformal generators. Okay, and all I wanted to say are just a bunch of things about this C. So sort of the physical implications of the central charge. So this is something that characterizes the conformal field theory. For free bosons, you get C equals to 1. For free fermions, you get C equals to half, and so on, different theories. In holography, we want C to be extremely large, etc. So it's some characteristic of the conformal field theory. And one physical way to see it is that it appears in the Casimir. So energy. So basically, if you put instead of considering your conformal field theory on the plane, you consider the conformal field theory on a cylinder. So the plane and the cylinder are related by conformal transformation. So you have something like e to the I omega on the cylinder is z on the plane, if I'm not wrong, something like this, divided maybe by the radius of the cylinder if you want. Okay, so you have an exponential map that takes you from the cylinder to the plane. And basically this anomalous term here enters into some anomalous transformation law of the stress tensor when you do such a conformal transformation. And what you find is that even though you had 0 expectation value of the stress tensor on the plane, you're in the vacuum, you're going to find a non-zero expectation value on the cylinder. So let me take just the plus component on the cylinder equals minus c over 24 r squared, where r is the radius of the cylinder. So if you wanted the physical interpretation of what the central charge does, well, it tells you that when you go to the cylinder, so you have to impose boundary conditions for whatever fields are making your CFT, you're going to pick up a contribution to the stress tensor, which is universal and is proportional to the central charge. There's somewhat related. So another interpretation of what the central charge means is that it's a count of the degrees of freedom of the CFT. So the larger the C is, the more degrees of freedom it has. And in particular, the entropy in the CFT is proportional to C times the temperature at large T. So if you go to high temperatures, you see that the entropy is proportional to T, but the proportionality constant is the central charge. And so in this sense, since entropy somehow counts what degrees of freedom you can be exciting, this C is counting degrees of freedom. I guess if you put it, yeah, so this has dimensions of 1 over length, so maybe there's an R here. Right. Okay. So now what I wanted to do.
Excuse me.
Yeah.
What's the definition of the entropy of a CFT?
Okay, so you have, I mean, so this CFT, so you have some energy levels, and you want to count the number of states in between some, well, so this is at finite temperature, so there's a similar formula for energy. Okay, so let's stick to the microcanonical ensemble where I can tell you. So this is just counting. So in the microcanonical ensemble, is just counting the number of states between two energy shells of energy E and E plus dE, and the number of states is going to be E to the S, which I can then transform to the canonical ensemble in the usual way. Okay, so now what I wanted to discuss, so there's something very, very nice about two-dimensional CFTs. So for a general quantum field theory and even for a general conformal field theory in higher than 2 dimensions, one does not know how to compute, so if the theory is strongly coupled, one does not know how to compute the entropy because of strong coupling. But it turns out that in 2-dimensional CFTs, one can use their very special properties to get a universal formula for the entropy at high energies or large temperatures. So this is something very, very special about 2-dimensional CFTs. There's a universal formula. So this is what I want to discuss a little bit about now, how one gets this universal formula. Which is something extremely special to 2-dimensional CFTs. And okay, so let me just discuss that. And it has to do, well, it uses both of these. So, okay. So to derive this universal formula for the entropy, one looks at the partition function for the CFT at inverse temperature beta. So Z of beta, which is trace of e to the minus beta h. H is the Hamiltonian over the Hilbert space, and here H is L0 plus L0 bar. Because these guys generate x plus and x minus translations, so this combination actually generates time translations. Now, this quantity, so if I go Euclidean, I can compute also this quantity via path integral. Okay, so let me assume that the CFT is on a cylinder with radius 1. So I have two coordinates, t and phi is identified mod 2 pi. Okay, so I put the CFT on a circle. Actually, in 1 dimension, it's known as a circle. Okay, and I can compute this partition function by weak rotating to Euclidean time and identifying it mod beta, where beta is 1 over the temperature, right? So I can compute this Z beta by the path integral with tau, which is, let me get the factor of i's right. Right. So tau is I beta. Wait, what did I do? Right. T Euclidean plus beta, and T is I times T Euclidean. Okay, so I'm computing some CFT path integral. So if I draw here so now my two-dimensional space, which is now Euclidean because I've rotated time, it has one coordinate which is phi, which is identified mod 2 pi, and another coordinate which is tau, which is identified mod beta. Right? So basically I have to compute the partition function of the CFT on a torus with this sort of identifications. Because if I take the plane and I do these identifications, what I get is a torus.
Excuse me, why you identify the two boundaries of the coordinate tau?
That's just the usual way to compute finite temperature partition functions. You make time Euclidean and you identify mod 1 over the temperature.
This is just the exactly point, but which I never answered. And I've said it many times how explicitly it's. I mean, every time because of the trace.
It's because of the trace. Yeah.
Then you use the sum over the endpoint.
This is take over the state, right?
The trace is taken over all the states in the theory.
And how it's directly related to the periodicity of the time?
Essentially, to have each of a particle itself. Okay, let's pretend that information maybe is not correct if you think about the consequences if you have states which are not periodic with periodicity beta, the phase equivalent, because it's only if you have states which don't have the good so if you have a state which has a good periodicity, then you sum over it anyway, it gives you one. But if you have, let's say, this kind of vector and you have period 2, period 5, and you get the classical manifold, the manifold nothing comes out. So the phase picks up all the things which have the periodicity. I think that's a very good understand. I think I don't know, maybe that's something like that.
Really? I thought this was very textbook. I can't pinpoint, but it should be done. Okay, I don't remember where I learned it from. But, for example. Anyways. So now the point is that since I'm just computing a path integral of the CFT on this particular Euclidean geometry, torus, it doesn't matter whether I label my, if I remember that this coordinate was space and this coordinate was time, because both of them are Euclidean right now. So in principle, I can just invert what I call time and what I call space. However, I have to keep the space periodicity fixed. Okay. So I can call this. Okay. So so now I want to call this space prime, and this I want to call it tau prime. But in doing this, I have to take care that the space periodicity is the same, 2 pi. But that I can do because because my theory is invariant under rescalings, I can only rescale my space and time coordinate by some constant, and the partition function will not be changed. So the claim is that this quantity is the same as this. So now I call this space, and it's identified mod 0 2 pi. But because so in order to get the right the rescaling, so to turn beta into 2 pi, I need to multiply this by 2 pi over beta, right? So I need to multiply both space and time by 2 pi over beta, and then I'll get the right periodicity of phi prime. But in this case, the periodicity of phi, which has now become my tau prime, is going to be 2 pi times 2 pi over beta, which is 4 pi squared over beta, and this is tau prime. Okay. So by switching the meaning of time and space in this Euclidean path integral, I find out that the partition function at beta is equal to the partition function at 4 pi squared over beta. Reinterpreting this as Euclidean time, and then its identification is going to be reinterpreted as a new temperature. But you see, this is very interesting. So beta was the temperature. So this tells you that the partition function at high temperature is related in a very simple way to the partition function at low temperature. So this is a very non-trivial relation that follows from this. Good. So now we're interested in beta goes to 0. So this is high temperature. Because I had to rescale the coordinates, and I cannot do that unless the action is invariant. So it's very important that that's conformal. Okay. So now I'm interested in the partition function at high temperature. So that's beta going to 0, because beta is 1 over t. And in this case, what happens? So if I go back to the trace interpretation, trace over the Hilbert space interpretation of partition function, I see that as one more step in between. Okay, so first I use this relation to relate the partition function as beta goes to 0 to the partition at 1 over beta. So this is going to be the partition function as this guy, beta prime, goes to infinity. Right? So beta prime, which is 4 pi squared over beta, goes to infinity. So this is low temperature. Okay? Now, given that beta prime is going to infinity, I go back to the trace interpretation of the partition function and then try to see whether I can evaluate it in this limit. And that's easy because as this beta, which is really beta prime, is going to infinity, the state that is going to correspond to contribute the most is the lowest energy state, because everything else is exponentially suppressed. So in the end, what I get is that z of beta, so for beta going to 0, is z of 4 pi squared over beta, which is approximately given by e to the minus 4 pi squared over beta, which is just beta prime, times the energy of the vacuum. Okay, so I just use beta prime equals to this quantity in order to evaluate my high temperature partition.
Are you assuming that the spectrum is gapped, or is this not?
I guess, yeah. Usually it's gapped, I think. Sorry, a gap in conformal dimensions. Sorry. Yeah, sorry. No, not mass gap. Good. Okay, good. So far we've gotten to this relation. So this is, as beta goes to 0, this approximates our partition function. And now we need to evaluate this E vacuum. But this E vacuum is actually universally computed by the central charge via this formula, because this was representing the expectation value of the stress tensor of the CFT on a cylinder, or otherwise known as a circle in one dimension. Okay, so we just have to plug in this formula for evac. And this was just the left moving energy. So I have to add to it the right moving energy to get the total energy. And I guess I also need to multiply it by some 2 pi. Do I have to multiply it by 2 pi? So this is just going to be minus C over 12. Oh yeah, sorry, because this is not really integrated. This H is just L naught plus L naught bar. L naught was that guy, so I get minus C over 24 plus minus C over 24 from the right, so this is minus C over 12. Okay, so this thing in the end ends up equal to E to the pi squared C over 3 beta, as beta goes to 0. So universally in the two-dimensional conformal field theory at high temperature, otherwise known as beta goes to 0, this is how the partition function behaves. Yeah.
So consider the left and right hand side of the partition function.
Mm-hmm.
Why they cannot be differed by some constant factor which depends on beta? Because seems to me, if we consider it in the passive integral point of view, we are doing a rescaling of the system, then the measure of the fields will also change.
Right. Right. But I guess, sorry, let me just get this right. So I guess under a pure rescaling, the measure doesn't change. Is that right? So under a more general conformal transformation, I have to be careful. But under pure rescaling, I guess the measure wouldn't change.
No, it will change, and the scaling dimension is not 0.
You're talking about anomalies, right? So I thought if all I'm doing is just a pure rescaling, okay, let me check this because I want to be sure, but I would say that under a pure rescaling of the coordinates, then I shouldn't be picking up this factor from the measure.
Yeah, you're using the global symmetry.
I'm using the global symmetry, exactly. So indeed, had I been doing some more crazy transformation than just a rescaling, then indeed I should be worried about whether the measure transforms, because there is an anomaly. But actually, just the pure rescaling part of the conformal group is not anomalous. And I'm only using pure rescalings to get from here to here. Does it make sense?
Well, they change by some global factors. Even for the global.
No. So the only reason that the path integral wouldn't be invariant under this rescaling is if there were an anomaly in dilatations, right? The action by itself is invariant by assumption because it's a conformal field theory under arbitrary conformal transformations. But I guess that the point that you're bringing is that the measure might not be invariant.
I think what it means is not the measure of field, like not the d5,
Mm-hmm.
the pattern group, measuring the pattern group, but the measure of dx.
What's dx?
Like in the action is the integral dx over the constant.
No, my question is
No.
defined now.
No, the action is obviously, yeah. So indeed, I think in principle you could be worried about the anomalous transformation of the measure. But actually, if you're just doing a pure rescaling of the coordinates, that part of the conformal transformation is actually not anomalous. But for something more general, indeed, you can be worried about it.
As I checked, the original definition of Z contains the Hamiltonian. So if the Hamiltonian is invariant under global symmetry, it should be okay.
Okay, good. So we got on here. And from here, I wanted to derive this universal formula for the end.
Theory that the way that the parameter is invariant, I mean, the scaling invariant, but not the full conformal invariant. Then how much can it push? To this duality, I suppose it holds.
In 2 dimensions, scale implies conformal. So there's scale plus Lorentz implies conformal. That's a proof. People have looked at something more weird where you just assume So you have translations, a plus minus, and you only have scaling of the x plus coordinate, but not of the x minus coordinate. And the theory is not Lorentz, so you don't have Lorentz. Sorry. Yeah, so this scaling implies that you have some combination of Lorentz and dilatation, but not the other. So Lorentz is broken, and you only have this rescaling. And then people can do some manipulations of the partition function to also prove that it has some sort of how do you call this? High temperatures are related to low temperatures. So that's a paper by Hartmann, De Tournay, and someone else whom I've forgotten. So they look at theories like this. But if you have Lorentz invariance, Lorentz plus scaling implies conformal, so you don't worry. Yeah. So the argument is, I mean, you have to do it carefully, but basically the idea is that if you have so you have translational invariance, so you have something like a current associated to x plus translations, d plus t minus plus equal to 0. So this is just, so as you know, the stress tensor generates translations. In particular, these components of the stress tensor generate x plus translations. And then when you assume that you have dilatations in x plus, so I'm using the light cone way of saying it, so splitting everything into plus and minus, then that current is x plus times t mu plus. So x plus rescalings is generated by this, and you look at the conservation equation for that. It tells you that t minus plus is 0. And then, since t plus plus has to be holomorphic, if you multiply it by any holomorphic function, not just x plus, but x plus to any power that you want, it's still going to be conserved, so you get an infinite number of conserved currents. So this is how you prove the Virasoro symmetry at the level. So you see, all you're assuming is translations plus scaling in x plus, and then you get the infinite number of currents, including the special conformal transformations. Okay, good. So I was. Yeah, so I'll just finish. I'll just write down the Cardy formula and okay, so now we want to get from the partition function to the entropy. So first we introduce the free energy. We use minus t log z. So this is minus t times pi squared c over 3, and beta is 1 over t, so I'm picking a t squared here. And then, so you have something like t ds is dE, and f is E minus ts. So from this you get that minus s dt equals df. So this implies that the entropy is minus df by dt, which is 2/3 pi squared c t. Okay, so this has already shown this thing that I was claiming, that the entropy is proportional to the central charge times the temperature at high temperatures. But now actually we want to write the entropy as a function of the energy, because that's what is going to be more useful. So the energy, well, the energy is F plus Ts Okay. Good. So what is F? Minus pi squared C over C t squared plus twice that. Okay, so I guess you won't kill me if I just write pi squared C over 3 t squared. So I get a factor of 2 from here and a minus 1 from here, and that's just it. And now I want to write this in terms of the entropy, because once I write it in terms of the entropy, I get the entropy as a function of the energy. So this is pi squared C over 3, and now I need T as a function of S, so that's 3S over 2 pi squared C squared. And with this, I get S, which is 2 pi squared C over 3 square root of 3E over pi squared C. Okay, so the pi squared here goes with 1 pi there. And let me put the C over 3 inside. So what I get is 2 pi square root of C E over 3, which is also okay, so now I want to write this in terms of L naught. So it's 2 pi square root of C and E. So in this case, I didn't consider angular momentum along the circle. So as you see, I only considered 3 trace of e to the minus beta h, but I didn't put a chemical potential for the angular momentum. So effectively, that was forcing me to have L naught equals L naught bar. Okay. So one can do this whole manipulations, which are slightly more complicated, by putting, adding some I theta j, where j is L naught minus L naught bar is the angular momentum. So the charge associated to d phi, which is d phi is dx plus minus dx minus, or something like that. So and go through this whole argument. But anyways, in this case, I only had L naught equals L naught bar, which was E over 2, because E is L naught plus L naught bar. So here I get 2C L naught over 3. And I want to pull the 2 out. Yeah, sorry about the manipulation. I'm making this a 4, and this is 3 times 2. And I'm going to suggestively write this as 2 pi square root of C L naught over 6 plus 2 pi square root of C L naught bar over 6, but in my case, L naught bar equals to L naught. And the reason that I decided to write it this way is because had I done the full analysis, including angular momentum, so L naught bar different from L naught, this would have been the formula for the entropy that I would have obtained. So if you want, you can do this as a homework exercise. Just add a potential for the angular momentum and redo this whole thing. You get a slightly more complicated torus. You're going to get a tilted torus in the complexation. But anyways, the argument is exactly the same. And what you get is that the entropy of a conformal field theory at high energies is given by this absolutely universal formula, which only involves the central charge, and L naught is E minus E plus J over 2, and L naught bar is E minus J over 2. So this is something very, very special in 2 dimensions for conformal field theory, that you have at any coupling, including strong coupling, you can write an exact formula for the entropy. This is rare and precious, but okay, so this is roughly the derivation. And it's known as Cardy's formula. Okay, good. So as Ricardo demanded, I'm going to give you a break. And after the break, we're going to basically, so this everything that I've done so far was in CFT. So after the break, I'm going to discuss how all these nice infinite dimensional symmetries of the two-dimensional CFT and the Cardy formula can be seen from a space-time analysis. So that really checks the duality in a non-trivial way. So usually when people write L naught and L naught bar, they refer to so this is not very clear notation. So on the plane, remember L naught and L naught bar were the dilatation and Lorentz generator. So x plus goes to lambda x plus minus. But now what we want to do is to be on the cylinder. So we need to do this transformation to go to the cylinder. So if my L naught was x plus b plus, in terms of the coordinate w on the cylinder, it's actually going to correspond to b w plus. Right? So what I had say dilatation operator. So the dilatation is L naught plus L naught bar on the plane becomes the translation operator on the cylinder. The same for L naught bar, which was x minus d minus becomes dw minus. Right. So this formula is written with L naught and L naught bar here, which are basically the conformal dimensions measured on the plane. But if we want to write in terms of energies and angular momenta on the cylinder, so this is why this is why L naught and L naught bar represent energies and angular momenta because of this map, even though we write it like this. And moreover, if we go to the cylinder, we have to take into account this shift due to the Casimir energy. So the L naught on the plane is related to the actual energy plus angular momentum on the cylinder by the shift of the 24. So this is the fluid flow. So I have to shift each of them by minus here. So in particular, in the vacuum on the plane, L naught is equal to 0, and well, this formula doesn't hold, of course, because it's So this formula holds for L naught and L naught bar much larger than C, because we derived it in the high energy, high temperature range. But sometimes it's important to include. Okay, good. So now what I was going to do, I was going to show how to see this formula and also the infinite dimensional conformal symmetry from a space-time point of view. So the setup, we just consider Einstein gravity in AdS3. So the action is 1 over 16 pi g integral d3x square root of g times r plus 2 over l squared. So the solutions to the equations of motion coming from this action are just AdS3. And if I want AdS3 over AdS5, this is the normalization. And okay, so this is sort of the universal low energy action for whatever theory of gravity that you might have in AdS. This is the leading term. So I'm just going to concentrate on this. Right, in principle, one can also have matter fields, like, not terribly massive scalars and stuff like that, but actually they won't affect at all the asymptotic symmetry group calculation that I'm going to present. They simply don't contribute, so I'll just stick to pure Einstein gravity. So okay, so this action is incredibly simple but still interesting. So first of all, it's well known that all solutions are locally AdS3. Okay, so so it turns out that Einstein's equations can be written as r mu nu equals to, yeah, sorry, I don't remember off the top of my head what all the constants were. Yeah, so the Einstein equation looks something like g mu nu equals some number over L squared times g mu nu. And then you can manipulate this into, so this shows that the Ricci scalar is constant. And then you can manipulate this to write just r mu nu equals minus 2 over L squared g mu nu, which I think is a correct equation. Okay. And okay, so one interesting solution to this is ADS3, which is the spacetime we discussed in the beginning for t equal to 2. But actually, it turns out that all solutions to this action have to be locally ADS3. And the reason is that in 3 dimensions, the Riemann tensor can be entirely written as a function of the Ricci tensor and the Ricci scalar. I didn't pull out, but it's something like r mu rho g mu sigma minus something with some coefficients plus r into g mu rho g mu sigma minus b antisymmetrized configuration, so something like this. So you can prove that actually this is just an algebraic relation in 3 dimensions. It's a consequence of the fact that the Y tensor identically vanishes in 3 dimensions. Okay, so this being given, if I impose now Einstein's equations, which are like this, it means that the Riemann tensor itself is going to be proportional to some number over L squared times g mu rho g mu sigma minus blah blah blah. Or this was the equation for ADS3. So this spacetime everywhere, locally it has to look like ADS3 because the Riemann tensor is expressible. Once I impose the onshore equation, the Riemann tensor is expressible in terms of the metric length. Like this. And probably this number is minus 1 if I choose my conventions correct. Okay? So a priori this looks like an incredibly boring theory. All the solutions are locally ADS3, so what can you do with it? But somehow the surprise is that actually this theory has very, the solutions can be actually topologically non-trivial. And actually we're going to find black holes and stuff like that, which, they're locally ADS3, but there's actually some non-trivial structure to them. Okay, good. So, yeah, so now I wanted to, so the goal is to compute the asymptotic symmetry group. And if you remember from the first lecture what the steps were in order to compute the asymptotic symmetry group, so these are the basically the group of large diffeomorphisms where large is qualified by whether the charges are 0 or not. One is to choose some boundary conditions. Some boundary conditions on the follow-up of the metric. As ADS3 is, has infinity, so as R goes to infinity, I have to tell you how the metric falls off with R. And then once you've chosen the boundary conditions, one has to find the coordinate transformations that preserve these boundary conditions. So these are the allowed diffeos. And then the next step was to compute the charges associated with these diffeomorphisms. So in the first lecture, I gave you a full formalism for computing these charges. So these were integrals over the boundary of the space-time of some appropriate quantity, which depends on the background metric, bar, and the metric perturbation, something like that. And check whether they are finite, integrable, conserved. And of course, one should also check whether they're non-zero. So if they're zero, that just tells us that the associated diffeomorphism is trivial. So what this will particularly mean is that if we're going to come up with some sort of asymptotic expansion for the diffeomorphism as a function of R, and then there are going to be some dots, higher powers of 1 over R, which are going to correspond to trivial diffeos, meaning things that will never lead to non-zero conserved charges. So we can just okay, and compute this, and then after we compute this, we just compute the symmetry algebra of these guys and try to see whether they form a nice algebra. So as we discussed, this is going to basically be given by the Lie bracket algebra of the associated diffeomorphisms, so we don't have to work too hard. But then there's a central extension that in principle can be there, and that we really need to compute by computing the transform. Okay, and I guess as I was saying in the first lecture, this choosing the boundary condition is a little bit of an art, because you have to choose them. If they're too lax, then your charges will diverge. That's not good. If they're too stringent, then your charges will be zero, which is also not good. So you have to sort of go, find exactly, guess the right thing in order to get something that both rich and not infinite. But usually a good way to go is to look at the fall-off of interesting solutions to the equations of motion. So okay, you have the vacuum, but the vacuum is boring. But if you have, for example, some black hole that's floating out, you look at the fall-off of the black hole solution, and then you're going to say, oh, okay, I want the metric to obey the same, to allow for all these black holes. So it's going to become clear. But usually the interesting solutions to the equations of motion sort of tell you what boundary conditions to choose, and then you can run the program. Okay. So as I said, okay, so now let's look at solutions to the equations of motion that are interesting.
Excuse me.
Yeah.
I don't know what means locally APS, I think.
Oh, it just means this thing that I was just erasing.
Okay.
It means that you can express the Riemann tensor as this particular combination of metric components at every point.
That's the definition.
That's, but then you can have non-trivial identification, so global constraints. So this condition in particular means that so remember that ADS had all these isometries forming SO2, 2. So at every point you're going to find Killing vectors. You're going to find so this has six symmetries. You're going to find 6 Killing vectors locally of the metric at every point. So and in vacuum ADS there are good, well-defined Killing vectors everywhere. What happens in the black hole spacetimes, for example, is that they're not going to be globally well-defined. So they're not actually isometries of the spacetime, but it's for, usually when a spacetime doesn't have an isometry, it's because the metric depends horribly on that coordinate, so locally you cannot solve the Killing equation. In this case, it's a bit more subtle because locally you can solve the Killing equation, so naively you think in any of the spacetimes I'll present, you have 6 Killing vectors, but actually global constraints tell you that actually for the black holes only 2 of them will be actual Killing vectors. So yeah. So this is this is a bit funny about three-dimensional gravity. Okay, good. So okay, so let me remind you what global ADS3 looks like. So we've written the metric earlier. So this was minus L squared times minus cos squared of rho d tau squared plus d rho squared plus C squared of rho d phi squared. So this was the general metric particularized to 3 dimensions. It's useful to introduce some coordinate r, to call this r squared. So which also goes from 0 to infinity. So then the metric looks like L squared minus r squared plus 1 d tau squared. This thing turns into dr squared over r squared plus 1 plus r squared d phi squared. Okay, so this is just global ADS. An interesting set of solutions that one can come up with. So I told you everything is locally ADS3, but then you can have funny identifications, or you can have conical singularities. So for example, if you try to put a particle in ADS3, it creates a conical defect. And these defect geometries, okay, so particles correspond to conical defects. And for this, the metric is something like this. So instead of 1, here I'm going to have some number smaller than 1, which I'm going to call it alpha squared. And okay. So basically what this metric does, okay, how do you see it's a conical defect? Right. I mean, in principle, it looks like this metric is identical to this metric. If I rescale, so if I let r equals r tilde times alpha, and I let tau equals t tilde over alpha, and I write phi equals phi tilde over alpha. Okay, I can completely absorb alpha into this rescaling, right? Because this picks an alpha square, which is eaten up by this guy. This guy is invariant, and then this phi absorbs the 1 over alpha from R. However, remember that these were global coordinates. So here in particular, phi was identified mod phi plus 2 pi. So you see that this rescaling is not completely innocuous. The metric in terms of the tilde coordinates will look identical to this, except that the identification of phi tilde is phi tilde plus 2 pi alpha, right? Because phi was identified mod 2 pi. So now if you look near the center of the spacetime, so let me fix tau constant, and I'm taking r to 0, so I'm really going towards the middle of ADS3. The metric is going to look more or less like that of a disk, dr squared plus r squared d. So I'm going to have, so near r tilde goes to 0, I have the metric looks something like dr tilde, so tau equals constant, dr tilde plus r tilde squared d phi tilde squared. So this looks just like the metric on the plane, except that my phi has the wrong identification. So the phi coordinate, so this is r tilde and this is phi tilde. The phi doesn't go around by 2 pi. It goes by some other number. So what this does is if I don't have the right coordinate identification, what I'm going to get is something like that. When I cut this, what I find is the plane where I just take this from 0 to alpha. Let's say that alpha is here. So I'm only getting this chunk of the plane. And I see there's a conical defect. Okay, and if I want these guys to be somewhat well defined, I should really be taking alpha to be 1 over some integer. Otherwise, I start going around it an irrational number of times. Okay. Good. So what I want to say. So this is the vacuum spacetime, and these are some conical defect spacetimes, which are very simple. And they basically correspond to putting particles in ADS, which create these sort of deficit angles. Now I wanted to compute the energy of the spacetime. And well, so in the first lecture, I gave you some very complicated formalism for computing the energy, right? So one had to compute these charges, this K, for infinitesimally closed geometries. And I mean, basically, this is, okay. What's nice about this formalism is that it's very general and very powerful. What's not nice about it is that I cannot do it on the board because I need Mathematica to plug in the expression for the charges, which you might remember was kind of long. So, well, so I was planning to give you a very nice and quick way to actually compute the energy in ADS, which is a different formalism. But that means that I will go. So if people are interested, I can talk about it's called the Brown-York stress tensor way of computing. So it's something that works for ADS and maybe some other spacetime. It's not as general, but you know, you can just stare at the metric and read off the energy from it, which is sort of nice. So, okay. So if people are interested, okay, these lectures take much longer than I thought, but you know, if it's useful material, I can certainly talk about it. Okay, so now I'm going to give you just a very quick way of, for example, computing the energy of these spacetimes, and you know, being able to compare the energy of vacuum ADS to the energy of these conical defect spacetimes. Okay, so I mean, it is completely equivalent to this formalism in the case of ADS, and in particular the way that you compute. I mean, it's just a different expression for the conserved charge, a different way to compute the conserved charge, but otherwise all these steps go through as before. I haven't changed anything in the logic. I'm just giving you a different formula. So this formalism is known as the quasi-local stress tensor, which you then integrate to find the energy of Brown and York. So I think this is early 90s, and it was very nicely adapted to holography by Krauss and Balasubramanian. And I can even, for that, I can actually give you the references. HepTH 9902121. So yeah, so in the context of holography, so this is, well, so I can tell you what the idea is here. So the idea, so as we discussed in the first lecture, in gauge theories and in particular in gravity, it doesn't really make sense to talk about local conserved currents because there's zero on shell. Remember, the Noether current for gravity was just proportional to the equations of motion. But it does make sense to talk about sort of quasi-local quantities that you can sort of integrate over some space-time region. So all of our charges were expressions that could be integrated over the boundary of a region, right? We're getting them by, if I have some spatial region sigma with some boundary delta sigma, this is where we're computing our conserved charges. So this Brown-York is sort of the same idea. And okay, so very vaguely saying, the idea is that you can compute the energy of a system by taking the derivative of the classical on-shell action with respect to time. Right? So usually you do your variational principle. You have some particle going from time 1 to time 2, and then you're keeping the endpoints fixed, and you can compute the classical action for that. So the classical on-shell action, now if you start to vary the time interval over which you're doing this procedure, what you're going to pick up is the energy. Now, now we have something a little bit more complicated. Okay, so how should I do this? So the setup is the following. So they consider some space-time, and they consider some sort of box inside the space-time. So this as usual is time, okay? And they're considering some spatial slice. And on the walls of the box, they're fixing the boundary conditions for the metric. So on delta sigma times time, which is the boundary of this box, they're fixing the metric, which I'm going to call gamma alpha beta. Okay? And now, so basically what they want to compute is something like the derivative of the on-shell classical action with this fixed boundary condition with respect to your appropriate notion of time. And the appropriate notion of time in this case, well, if you just had gamma 0, 0, so the time component, this is usually the lapse, something like this. So it would be the derivative of the action with respect to the proper time would be some sort of derivative with respect to this n. So very, very roughly speaking, I'm not giving any sort of precise argument. They're claiming that the way that you may be computing the energy is by introducing a stress tensor, T alpha beta, which is delta S on shell, which depends on these boundary conditions gamma that you've put on the metric here, by delta gamma alpha beta. And I think there's minus 2 over square root of gamma. Okay. Minus signs fluctuate between Euclidean and Lorentzian. I think in Lorentzian it's minus, but I'm not. Okay, that's something to be checked. Yes.
I mean, probably this equation. I'm thinking about classical mechanics. I have a Lagrangian, and I change it by the total derivative, and the action changed by the value of this. Of the function I take the total derivative. So the energy seems to be defined.
So when you change the time interval between
No, I have a Lagrangian.
Yeah.
I change my Lagrangian, L becomes L plus d over dt of f. And the action is the initial action plus f, which depends on time.
Oh.
So in some sense, we have to fix the action that I don't see at all.
Sorry. Sorry. So when I add. Okay, so you're saying somehow that the expression for the energy will change if I change my expression for the Lagrangian by this d by the dt of something. That's what you're saying. And then I need to think about it. Do you mind if, yeah. Okay.
I am a bit confused about that formula. It's because suppose I have a particle in some potential, but I really get from that derivative is the Lagrangian, not really the energy.
Yeah, but then you have some boundary term from the endpoints.
Just a normal potential is close to or minus d of x. Then the action, if I just take the derivative, I get the Lagrangian.
Yes, but then you have to look at the variation of the endpoints, and that's going to give you a PQ dot.
Okay.
A minus PQ dot, so it's going to give you, what you're going to get is L minus PQ dot. Okay, I mean, this was very, very rough. Okay, and I need to think about that, but okay. Very, very rough motivation for writing down this expression for the stress tensor. Very rough. But okay, once you have a stress tensor, you know how to compute energy. So this stress tensor lives on this boundary over here. And now, in order to compute whatever conserved quantity that you want, in particular the energy, you're just going to integrate over this delta sigma. So this is at the boundary of sigma on a fixed time slice. You're going to, okay, okay, let me call this an n-dimensional spacetime. So this is going to be n minus 2 x square root of sigma, where sigma is the induced metric on the surface, into the normal and alpha at the surface, into T alpha beta, into your favorite diffeomorphism. Okay? And these charges will be conserved provided that this is a, so if you have, yeah, in the case of the ADS, okay, so in general, T is conserved, so the charges are conserved provided that Xi is a Killing vector of the boundary metric, right? Because that would be, so if I compute the alpha beta, so this is the usual argument. You start moving up the surface, you compute the difference from the integral of the divergence over the little band that you get over here. And that will vanish provided that this quantity vanishes, right? So this is conservation. So when this guy acts on this, it gives you 0 because this stress tensor is conserved. Plus T alpha beta del alpha Xi beta. And so because this is symmetric, you only get the symmetric contribution here. So if, in particular, Xi is a Killing vector of the boundary metric, this term will also vanish for an arbitrary symmetric T. But if it so happens that T is traceless, which will be the case in our case, then you can also have the alpha Xi beta is proportional to gamma alpha beta times some number. And this will give you the trace of the stress tensor, and this will still be conserved. So this is generally conserved for T symmetric, and Xi a Killing vector of the boundary. But if T is traceless, then it's enough for it to be a conformal Killing vector of the boundary. Okay, good. Yeah.
The conservation of the stress tensor.
Mm-hmm. The conservation of yeah. So in particular, in the case of ADS3, you can see very, very explicitly how the because this will now become the conformal boundary, so we're going to be at R goes to infinity. So in that case, okay. and then solving the Einstein equations order by order in 1 over r will impose constraints on the divergence of T and on the trace. Yeah, that's entirely correct. Okay, so what do I want to say now? What do I want to say? Yeah, so the Brown-Jost tensor is given by a very simple formula. So as I say, what they want to do is that they want to consider the stress tensor like for this box region, and they want to fix the metric at the boundary of the box. In order to be able to do that, they should better have a good variational principle, in the sense that delta of S on shell is proportional to delta gamma alpha beta. Because if it's not proportional to the metric, to the variation of the metric on the boundary, then they cannot fix the metric. So this is as usual. You how to say? It's okay. For example, if you have a system, a classical system, and you have x and p, you can fix x at the boundaries of your integral, but you cannot fix both x and p. Right? That you wouldn't be getting any non-trivial solution. So they want. Okay, so they want to compute the on-shell action. So the on-shell action. So we just have Einstein gravity in the bulk. So S is 1 over 16 pi g integral of. This works in any dimension actually, but so you can put d here if you want. R plus. But then it turns out that so if you're computing the variation of this Einstein-Hilbert action, where you try to fix the metric on the boundary, you're going to get terms that are both proportional to delta gamma alpha beta and to the normal derivative of gamma alpha beta. So in order to have a good variational problem, what you want to do is to maybe add some boundary term, because some boundary term will not change the equations of motion, given that it's a boundary term, that would cancel the variation of the normal derivative. And it turns out that the boundary term that you have to add is the integral of the extrinsic curvature of the boundary. So this is an integral of a d2x of square root of gamma into k. So gamma is the induced metric on the boundary, and k. Okay. So k basically tells you how this surface, the boundary, is embedded in the other part of the spacetime, and is given by a half the Lie derivative along the normal vector to this surface of gamma alpha beta. Okay, so this hypersurface it's a codimension 1 hypersurface. This thing, it has some normal vector to it, which is the guy pointing like that. Actually, we want the outward pointing one, so we want actually that one. So this is. Okay, let me call this n tilde to not confuse with this guy, which is a different normal vector. So n tilde is just the normal vector that points out to this surface on the boundary. Okay, and okay, so the derivation, you can find the derivation of this term. So this is called the Gibbons-Hawking term. And you can find the derivation for it in Wald, for example. I think Appendix E. You can find exactly this argument that the on-shell action doesn't have is not proportional to delta gamma alpha beta, and how you derive this factor with the correct coefficient. Anyways, so once you've defined the correct on-shell action that only depends on the boundary metric gamma. So when I vary it, it's only proportional to delta gamma, but I don't get normal derivatives. So the normal derivatives can be anything that they want. the Brown-York stress tensor is simply defined P alpha beta Brown-York is minus 2 over square root of gamma delta S on shell. So how do you say, Einstein-Hilbert plus Gibbons-Hawking, the full variation of the action divided by delta gamma alpha beta, because this guy is actually proportional to it. And then, okay, and then if you, well, it's a long computation to figure out what the variation of this R was, but the end result that you get is something like 1 over 8 pi g. Where did I write it? Okay, I haven't checked my factors. So you should check whether there's an 8 and whether there's a minus sign or something like that. K alpha beta minus K gamma alpha beta times, is there a square root of gamma? No, I guess there's no square root of gamma because I divided by it. Okay, so this is the Brown-York stress tensor up to factors that I wasn't super careful about, but I hope this is, anyways, this reference that I gave you should have the correct factors. Okay? So this is after including the variation of R and the variation of this K here. Now, how do you apply this to compute the energy of some sort of spacetime that's asymptotically ADS? It turns out that this expression is divergent. So okay. I'm afraid that I might go until 12:30 just to finish the Brown-York stress tensor and compute the energy of the spacetimes, and if people are not too starving. Okay, good. So now we want to apply this to just ADS, and the only problem that we have with ADS is that it's well, it blows up asymptotically. So we have to do something about that. And in order to give you a universal formula, I should tell you how I can write the most general ADS solution. So actually there's, it turns out that there's a very simple formula for the most general solution to ADS3 gravity, which is obtained by solving the equations of motion, order by order in the radial coordinate. So okay, so let me just say one thing. Okay. So if I just solve the equation R mu nu equals minus 2 over L squared G mu nu, I want to solve, I want to find the most general solution to this equation. Okay. And to find it, it's useful to go to some convenient gauge. And people pick a radial gauge. And in the radial gauge, I can write the metric as ds squared equals dr squared over r squared. So this is not quite a radial gauge because, well, radial gauge would be d log of this r, but okay, never mind. Plus gamma alpha beta dx alpha dx beta. So I have no mixed components of the metric between the radial and the boundary coordinates. And it's very useful that I've deleted my drawing. But here what I have, so this is the radial coordinate going like this. And gamma alpha beta is really living on the boundary of the ADS spacetime. Okay, so now one can look at the just the Einstein equations and what do they tell you about the form of this gamma alpha beta. And what you find is that gamma alpha beta has some expansion, which is r squared times g0 alpha beta. So this gamma alpha beta depends on both R and X alpha, where this G0 only depends on X alpha, X rho. Okay? Plus something that looks like G2 alpha beta, which only depends on the X's, plus 1 over R squared G4 alpha beta, which only depends on the X's. Okay? So once you go to this, and it turns out that the expansion finishes here. So this is very, very special of ADS3. You only get 3 terms. If you go to radial gauge and solve Einstein's equation, this is the full solution, where I have to tell you what are these G0, G2, and G4. So it turns out that G4 is entirely determined by G0 and G2. It's something like 1/4 G2 alpha rho G0 rho sigma G2 sigma beta, something like this. G0 is arbitrary. And G2, part of G2 is determined by G0. And since I didn't do my homework, I cannot tell you what the factors are, but the trace of G2, so I do G0 alpha beta, G2 alpha beta, so this is trace of G2 is proportional to the Ricci scalar associated to the boundary metric G0. So this G0 is called boundary metric because it's the coefficient of the most blowing up part of the metric.
Yes, I think the powers are the opposite.
R goes to infinity. I'm keeping the same conventions as over there.
7 goes to 0.
I can choose R such that it goes to infinity at the boundary. And this agrees with that convention. So I guess what Adam is referring to is that people usually, I mean, these are sometimes called Pfefferman-Graham coordinates, and people usually use R equals 1 over Z, where Z goes to 0 at the boundary, which are the more usual conventions. But I mean, you can do it either way. Okay, so what you find is that the trace of G2 is proportional to the Ricci scalar of this boundary metric, and you find that delta alpha G2 alpha beta, I think it's going to be proportional to, so I think this is minus some number times G0 alpha beta R naught equal to 0. Something like that. Okay, so this refers back to your question about, obviously we're going to find that the components of the stress tensor are related to these metric components, and this is how the Einstein equation actually fits. So because this comes from the Einstein equation, and I should also mention Skenderis, Kostas Skenderis did a lot of work on this, and he discusses how you solve the Einstein equation order by order in the 1 over R expansion and so on, and you can find all of this in the literature. Minus, I don't know, everyone seems to have crazy conventions, so I'm working in convention-free. But you know, if you want to prove yourselves, you should find your favorite set of conventions where all the signs work. Okay, good. So now I just wanted to compute this.
Is this, if you have matter as well, do you still have this one?
Well, then you're not solving this anymore.
Okay,
So if your matter, if you have very low mass scalars, they might be important near the boundary, and yeah. But usually for yeah. Good. So now the stress tensor. So I want to compute that stress tensor. So and this is the expansion of my metric. And as I said, k alpha beta is 1/2. And now I need the normal to this boundary, and the normal vector. So it's the normal to the boundary is at r equal to constant. So the normal vector, this n tilde, with lower index mu, is going to be proportional to dr. Sorry, d something like that. right? It's only going to have a component for mu equal to r, because it's going to be d mu of the function that I'm setting to a constant on that hypersurface, and that function is r. Okay, so and if I want to normalize it, this and let me put upper mu is going to be something like r dr. So this k alpha beta is going to be r dr of, and now I'm plugging in this full. I'm not sure I said this. This is known as the Fefferman-Graham expansion. It's also valid in higher dimensions. What happens is that, well, the interpretation of the metric components changes, but you have exactly the same thing in higher dimensions. So r dr of r squared g0 plus g2 plus r to the fourth g4. So this is going to be r squared g0 alpha beta plus 2, what have I done? 1 over r squared, right, minus 1 over r squared g4. Okay, and then k is really gamma alpha beta into k alpha beta. So notice that there's no g2 factor here because it had no r dependence. Okay, so now I have to invert this metric, and let me assume that I'm going to pick up an 1 over r squared times g0 minus 1 over r squared g2 plus blah 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 into k. And it should be clear that since my boundary is that r goes to infinity, I only care about the terms that are finite as r goes to 0. So I'm going to drop everything that's not finite as r goes to infinity. So so k. So when I multiply this guy by this guy, I get the trace of g0. So that's 2 because I'm in 2 dimensions. And then this term is going to be too small. But then, okay, what have I done? I also have, sorry. I guess I also have a square root of gamma here. Okay, to check. But this is 2 times, oh my god, minus g2, no, maybe this one, okay. 2 minus, okay, sorry, what is this? This times that is minus 1 over r squared g2 alpha alpha, where I've contracted with g0. Okay, so this comes from this term contracted with that term. And this term is way too small. It goes down like 1 over r to the fourth. The reason that I cared about 1 of the r squared is because this guy blows up. So I'm going to multiply this k by this blowing up guy, and that's not good. Okay, so in the end, what I find is that T alpha beta Brown-York is 1 over 8 pi g times, so this k, which is r squared g0 alpha beta, this term I'm dropping, minus g0 alpha beta times r squared plus g2 alpha beta times 2 minus 1 over r squared trace of g2. And you immediately see a problem here. The problem is that this is 1 r squared minus 2 r squared, so this stress tensor actually blows up as r goes to infinity. So it needs to be renormalized. So actually, before renormalization, there's regularization. So I need to impose some cutoff in my boundary at r equals to rc, where rc is some large fixed number. So this has allowed me to do all these expansions. So all r's are rc's here. But now I have to somehow get rid of this divergence that I find in the stress tensor. And the game is that basically what you do, you're allowed to add any sort of boundary term, because that doesn't affect the equations of motion, as long as it respects the variational principle, because we want delta S total to be proportional to delta gamma alpha beta. So in principle, I can add any functional of the boundary metric gamma alpha beta that's going to respect both the equations of motion and the variational principle. And I can choose it in such a way as to get rid of this ugly divergence that I have here. And the counter term that's added for ADS3 is, where did I write it? Is, oh my god, minus 1 over 8 pi g L integral d2x square root of gamma. Okay, did I miss something? Okay, sorry. I think I missed some factors of L, so I had the factor of L squared here, which might propagate into all the formula factors of L. I'm really sorry. But this implies that, well, what happens? The n lower, so I guess, yeah, there's going to be a 1 over L in n, which presumably translates into 1 over L here. Otherwise, I just set L equal to 1 and not bother you. But okay, let's pretend this is correct. Good. So now when I add this counter term, it's not going to affect the variation principle, but it is going to contribute to the stress tensor, because delta square root of gamma is minus a half gamma alpha beta delta gamma alpha beta times square root of gamma. And taking into account the fact that the stress tensor has some factor of 2 in the definition, presumably, okay, my notes are really unreadable. I'm really sorry. This is why this isn't quite working. But it should add a plus gamma alpha beta. Okay, I'm going to add a plus gamma alpha beta, and if it doesn't work out, it means I added the wrong factor. So the 2 goes into the definition of the stress tensor. And the minus with the minus gives me a plus. But there was an overall minus. Okay, so maybe it's a minus alpha beta. Okay. Anyways, no, it's going to be a plus. Okay, please figure out the sign because I missed it. But anyways, so it's clear that up to a sign, this counter term will give you the correct stress tensor. So T alpha beta renormalized is going to be 1 over 8 pi GL, because I missed the factor of L, K alpha beta minus K gamma alpha beta plus gamma alpha beta, where this guy comes from the counter term. And you see what happens. This gamma alpha beta is going to add plus r squared g0 plus g2 here. So this is going to cancel the minus 2. So this guy with this guy cancel against the 2 here. So that's nice. And what I'm going to pick up is a g2 minus 2g2. Don't tell me I'm getting 0. No, this is trace. Okay. Yeah. So I guess I had an overall minus sign over there, but T alpha beta roughly comes proportional to minus G2. So I get a minus 2 from here and the plus 1 from here. So it's minus G2 alpha beta. And then I have a minus, with the minus is a plus, and I get a G0 alpha beta times trace of G2. Okay? So this probably fixes the signs. Also, it means that my Brownian stress tensor actually differ by this expression by a minus sign, and then the counter term was correct, but since the whole thing, anyways. Because I'm supposed to get these things with a plus. So there should be an over or minus sign. Okay. I'm sorry about this, but you get the idea. What we get in the end is some expression for this holographic stress tensor, which is completely finite. It only depends on this G2 and minus its trace. And actually, these nice relations that G2 obeys, that are imposed by Einstein's equation, translate precisely into conservation of the stress tensor, because it satisfied precisely this, and this guy turns out to be nothing but P alpha beta. And the trace relation actually gives you the correct conformal anomaly. So you can actually read off the central charge. I haven't talked about this, but you can find it in the Di Francesco. The conformal anomaly translates into a non-zero trace for T mu mu, which is minus C over some number, probably 24 times R of G0. And you can just read it off from this holographic expression plus what follows from the Einstein equation with the correct coefficient here. Good. So all this song and dance was in order to give you a really simple way to look at the metric and read off what the energy is. Which I'll do now and then stop. So if I want to read off the energy, for example, of global ADS, now it's very simple. All I need to do is to go to radial gauge, such that this term looks like dr squared over r squared, and read off the coefficient of the term in the metric that does not depend on GTT, on R, right? Because that was the definition of G2. And the claim is that even if I do that coordinate transformation to radial gauge, this will not matter much. The term that's constant in the metric, so whereas usually I have to do it, here I think I don't. And I can just read off G2, which only has a tau-tau component, which is -1. So this will imply that the stress tensor only has a tau-tau component, which is -1 over 8 pi GL, something like this. And when I try to compute the energy, it's just going to be 2 pi times this guy, because my coordinates identify with 2 pi, so it's -1 over 4 GL, which, okay. In units of 4 GL, the energy is -1. Let me put it like this. But now, you can also read off the energy of these spacetimes. So you fix the boundary metric, so you have to use the same boundary coordinates with the same identification. So I really have to work in this form of the metric for the conical defect spacetimes. And then I just read off the only the coefficient of r to the 0 term in the asymptotic metric expansion. When I tell you that this the transformation doesn't matter, it's just minus alpha squared. So what we get is that the stress tensor for conical defects is something, okay, in the same units is going to be minus alpha squared. But alpha was 1 over n, so it's going to be minus 1 over n squared. Good. So, yeah, so before I had argued that in order for this conical defect to make sense, the deficit angle had to be 1 over some integer. So this is where this guy comes from. So, okay, so we've used this method to really get the the lower part of the spectrum of solutions in this ADS3 spacetime. So we have the 0 of energy here. And then we have global ADS somewhere here. And I'm very sorry that I didn't compute this, but OK. So you have global ADS at energy -1 in some units. And then you have all these other spacetimes at, -1/4, -1/9, and so on. All the conical defect spacetimes sit somewhere here, accumulating to E equal to 0. OK? And I should say that the fact that the energy of global ADS is negative is very nice, because this is really, we're putting the boundary CFT on a cylinder. We have a compact coordinate on the boundary. And that matches nicely with the idea that we have a dual CFT, where we also know that the energy of the theory on a cylinder is negative. So if I had, in principle, I can get my numbers right and show to you that this is precisely -c/12, which is the Casimir energy. But given the current state of missed conventions, I think I'll do it in the next lecture. OK. So you see, so this is vacuum ADS on the cylinder, importantly, has negative energy. And then you have all these conical defects which sort of accumulate. And then next lecture, I'm going to explain to you where the black hole sits. So the black holes somewhat sit at positive energy somewhere here. And that's the spectrum, which matches nicely with what you expect in the dual CFT. OK, I'm really sorry to have kept you so long. And we'll continue next time.